Welcome to the video tutorial for Unit 9, Day 1. Today we are going to be covering pages 1 through 4, and you need to make sure that you have your notes with you. If you are absent, then make sure you're trying to figure out what those notes are. Get those from your teacher or from a classmate. Okay, I'm not going to answer these ones for you, obviously, but I am going to circle some keywords here. Okay, when we're talking about heat transfer, which would be conduction, convection, and radiation, these are the keywords: contact, waves, and currents. When we're talking about exothermic and endothermic, the key words are either absorb or release when we're talking about heat, okay, or heat or energy. And then randomness and disorder, this is a new word for us, entropy. Okay, that's a law of the universe that we haven't really gotten into much, but disorder is entropy. I will have you guys do that one. Okay, I'm going to do this column for you. We're going to do those together, and I'm going to let you check your answers on these ones. So when we're talking about is it matter or energy, matter is anything that has mass and takes up space. We learned that back in Unit 4. Okay, so dirt, obviously you can see it. It has mass, it takes up space. That's considered matter. Water, H2O, has a mass of 18.015 grams per mole. So we know it has mass. An electron has mass and takes up space. It's very, very small, but it does have mass. Okay, heat does not have mass and does not take up space. Heat is a kind of thermal energy. It's a electromagnetic wave. Air is made up of things like water and oxygen and nitrogen and carbon dioxide, all of which have mass and takes up space. Oxygen, we know, has a molar mass of 15.999, so it's considered matter. And sound. Sound does not have mass and does not take up space. So in this column we have two things that would be considered energy, not matter. In this column there are also two things that are considered energy. The rest are considered matter. So see if you can find them. Okay. Let me just give you a hint on this one. Electricity is a stream of electrons. So I'm just going to go ahead and write a current of E negative electrons. So using this column should help you answer that. When we're looking down here, okay, we did our notes on this. We've done notes on this before today too. When I have a solid and it's moving to a liquid. Okay, so a solid, I always like to think of water. So solid water is ice. So if I have ice and I put it in my hand and it turns into a liquid, as I hold that ice, it's going to feel very cold to me. And that is melting, right? Okay, when ice turns into a liquid, it melting, that's going to feel cold because it is endothermic. Now that's not a great example because ice itself is just cold. But when we're doing the opposite of that, so if I have a liquid moving into a solid, so liquid water turning into ice is called freezing, right? Now I'm going to recommend that you write this down here at the bottom. Our three states of matter that we really focus on are solid, liquid, and gas. Okay. Anytime we're moving this direction, we're getting more disordered from our organized solid particles to our super random gas particles. Anytime we're moving in that direction, it is considered endothermic. Okay. Just like this one, solid to liquid, this way is endothermic. Anytime we're moving this way and we're getting more organized, from our random gas to our organized solid, it's considered exothermic. Okay, so endothermic versus exothermic. So freezing, we're going this way. We're going from a liquid to a solid, so that's going to be considered exothermic. Okay, so go ahead and, using this kind of reference chart, see if you can fill in the rest. E and F are a little bit strange. Going straight from a solid to a gas, you're probably going to need to look that up in your notes, the name of it. Okay, you should be able to do endothermic, exothermic with this, but check these phase changes in your notes. Okay. Let's look at page 2. Page 2 gets a little bit interesting. Some of them can be not quite as clear. We're going to look at a few of them. Remember, the key for conduction is contact or touch. Okay? So if I put my hand on a piece of ice and I physically touch it, that's conduction. Convection would be if I held my hand up over the top of the ice, I could feel the cold air circulating. So I'm going to put currents. Okay, hot air rises, warm air sinks kind of idea. And radiation is when heat moves sideways or like from a fire. The way that heat moves out in electromagnetic waves. Okay, so hot coffee is stirred with a spoon. The spoon gets hot due to the fact that the spoon is in the coffee, it's touching the coffee, which would make it conduction. I'm just going to go cond like that. We can just do C-O-N-D. Okay. A certain type of decorated lamp, lava lamp, right, contains colored liquid. The liquids form globs that break off and rise to the top. Okay, so as it gets hot, it rises due to convection, C-O-N-E. Okay. Near the ceiling of the room, the air is warmer. Warm air rises in currents because of convection. Okay. A college student holds his hand near an iron. It doesn't say above an iron. It doesn't say he touches the iron. Okay, he's just putting his hand kind of close to the side of the iron, and he can feel the heat radiating off of it. Okay, so that'd be radiation. I'm going to let you write that down. E, certain type of stainless steel cookware has a layer of copper applied to the bottom to help it heat evenly. Okay, so that copper is touching the stainless steel. See if you can answer that one. F, in a swimming pool, the water near the surface is warmer. Warm water rises because of. Okay, that's a current. See if you can answer E and F. The house burns down. Across the street, the vinyl siding is twisted and warped by the heat. So that's across the street. It didn't rise from it. It didn't touch it. Okay, that's radiation. R-A-D. Radiation. The waves is transferring out from the fire in all directions. Okay. So see if you guys can take a look at it. I just want to look at J and K. A huge rock at the state park gets so hot during the day that you can't sit on it because of, that would be radiation from the sun. The heat from the sun, that's why it's heating up. Okay, there's nothing touching it. It's on the ground. You lay on the same rock at night so that you can get warm. So now you're going to sit on the rock in K. And as you touch it, it's keeping you warm because of conduction. Okay, so look at those other ones on your own. See if you can kind of figure that out. 5, 6, and 7, these are very similar to test questions. So when you walk on the beach in July, the sand feels hot because no heat is transferred. No, it feels hot because heat's transferred. Heat is absorbed into your feet from the sand, so it feels hot. That one looks pretty good. Heat is transferred from the ocean to the sand. Usually the ocean's colder than the sand, so that's not right. Heat is absorbed by the sand from your body, leaving you feel hot. Okay, and that's not it either. Heat is going to go from the hot sand to you, which is why you feel hot. It's absorbed. B. Okay. Take a look at 7 and 6. For number 7, you might want to turn back and look at that little key we made ourselves here. Okay, when it condenses or freezes. See if you can figure that out. Okay. Number 8, I'm not going to really have my students talk about plasma much other than K. After the critical points, okay, that's plasma. Otherwise, you can kind of ignore plasma for this. Just say solid, liquid, or gas. Okay. The highest kinetic energy. Okay, kinetic energy is just movement. It's also the highest temperature. Okay, so solid, liquid, or gas. Technically plasma if you want, but we would say gas and maybe plasma. But gas is more important. The most dense organized state. Okay, that's going to be our solid. Produced after sublimation. Check your notes. Can change volume. Well, that could be both. So, solids don't change volumes, liquids don't change volumes, only gases change volumes. Shape does not change, that's solid. Has the least entropy. Remember, entropy means disorder, so F and L are actually the same question. Which one is the least entropy or least disorder? Which one's the least disorder? See if you can figure those ones out. Okay. Check your notes, try with your groups, see if you can get some help. Okay. Number 9, place the states of matter in decreasing order from most disorder to least disorder. Okay, so it means most random to least random. So the least random would be solid because the particles are all neat next to each other and holding still, solid. The most random is going to be super random gases or plasma. So we should go plasma, gas, liquid, solid. See if you can find that choice. From most disorder to least disorder, to organized. Okay. See if you can take a look at 9 and 10 using your notes. That's page 3. Let's switch over to page 4. Page 4, you're going to need your calculators. Okay, we did this at the very end of our notes. Okay, it's asking you, is this graph showing endothermic or exothermic? So what we have is energy here. You can think of it as temperature. That's all right. They're showing that we're starting at 60, we got this little hump, and then it's like a roller coaster, we came down. Okay, so from my starting point right here, I'm going to call this initial. That's my initial temperature versus my final temperature. My final temperature is lower, which means energy isn't being created or destroyed, because it can't be created or destroyed. It's conserved. It means energy is leaving. It's being released. If my energy came down, it's because that energy was given away. And giving away or releasing energy would be exothermic. It's releasing or giving away energy. Delta H is always final minus initial. Okay, final minus initial. So in this case, my final is 30. If I go like this and I come over, it's 30 right there between, 50. 40, 50, 60. So I have 50 minus 60 equals. Okay, and be careful how you enter that into your calculator. It does matter. 50 minus 60 equals negative 10. So please make sure you are writing negative 10. And if you look right there, your unit is kilojoule, kJ. So there's your final answer. Okay, final, the lowest point, or the last point minus the beginning point. Final minus initial. For activation energy, it's the highest point minus the starting point. So it's the highest point minus the initial points. So the highest point on this one is 80, minus the starting point is 60. 80 minus 60, minus 60 equals 20. So my answer is going to be 20 kilojoules is the activation energy. Okay. That's how you're going to go through. For this one, you're starting at about 15, it looks like. 15, and we're ending at 30. The highest point looks like it's at 45. Okay, so those are the numbers we're going to be using for B and C. And the energy is starting low and ending up higher. So the only way my energy can come up is energy is being absorbed. Energy is going into the system or entering the system. Entering. Oh, okay. Make sure you're doing final minus initial here. Be careful if it's positive or negative. For this one, it's the highest minus the initial or the starting. Okay. And activation energy should always be positive. If you didn't get a positive activation energy, you're doing something wrong. All right. Great job, y'all. Make sure you're finishing up pages 1 through 4.